This lesson explains how to work with array and waveform data types with single-channel and multi-channel acquisition data. The array data type is a collection of data elements of the same data type. For example, the following figure shows three different arrays: a numeric array, a Boolean array, and a string array. Each item in the array is called an array element. This example array consists of 10 array elements. Each array element has a corresponding index number that specifies the array element's location within the array. The first array element has an index of 0. The second array element has an index of 1. The third array element has an index of 2, and so on. The array element at index 6 has a value of 27, and the array element at index 9 has a value of 30. Arrays can have one or more dimensions, for example, length, height, or depth. The top side of the figure shows a one-dimensional array, which extends in only one direction. The bottom side of the figure shows a two-dimensional array, which extends in two directions, so we have rows and columns. The 2D array shows its array elements in a grid of rows and columns. A 2D array has both a row index and a column index, which both start at 0. You can specify a specific array element using the row index and column index. For example, the highlighted array element is at row index 0 and column index 6. You can also specify an entire row using the row index. In the same way, you can specify an entire column by specifying the column index. This figure shows an example of how a 2D array is visualized by an array indicator and a graph. The graph interprets each row of the 2D array as a separate plot. An empty array has a defined number of dimensions and defined data type, but contains no data in its elements. The empty array in this example has 2 dimensions and has a numeric data type, but it contains no actual data. An initialized array has a defined number of dimensions and data type and also contains data in its elements. The initialized array in this example has 2 dimensions, with 2 rows and 3 columns of defined numeric data. Note, the visible elements in the array shell are only a part of all the array elements. Use the vertical and horizontal scroll bars to explore the whole array. To create an array, I'll add an unconfigured array to the front panel and then rename it. Next, I'll define the data type of the array. To make a numeric array control, I'll place a numeric control inside the unconfigured array. To resize the array to show 6 elements, I can drag either of these blue dots. Because this is a 1D array, I can only resize the array in one direction. Notice that the 6 elements appear grayed out. This is because the array is empty and does not contain actual data. I'll enter data in the array control. This is the array index display, which controls which array element is shown at the leftmost element. Right now, the element at index 0 is shown here. The element at index 1 is shown here. Notice how the array index display affects which elements the array control shows. Now I'll wire this array control to a graph indicator and run the VI. Notice how the 1D array data is visualized in the graph indicator. I can right-click the plot legend and configure the visual style of the plot. I can also rename the axes on my graph. As you can see, here's the array data point at index 0, and the array data point at index 1, and so on. To create a two-dimensional or 2D array, you must change the number of dimensions from 1 to 2. You can do this either by right-clicking the index display and choosing Add Dimension, or just resizing the index display. I can resize the 2D array to show a grid of rows and columns. Now I'll enter data into the new rows. Notice that the index display now shows two numeric controls. The top numeric control refers to the row index. The bottom numeric refers to the column index. Let's run the VI. Notice that each row in the 2D array represents a separate plot in the graph indicator. Click each plot in the plot legend to configure it. The waveform data type is made up of three items. Start time, T0. This specifies the start time of the waveform. Time interval between data points, dt. This specifies the time interval in seconds between data points in the waveform. Data values, Y numeric array. This specifies the data values of the waveform. You can visualize the waveform data type using a waveform indicator or graph. The data values in the Y array represent the data values at each point. The T0 start time item and the DT interval time item in the waveform data type provide timing information. Because of this, the x-axis for a graph with a waveform data type is in units of time. The dt, or interval time, specifies the time interval in seconds between data points in the waveform. If you need to extract the individual Y-array items, the T0 or DT waveform items, then use the Get Waveform Components function to access the specific item. Let's examine the waveform data type. In this VI, the waveform control passes its data directly to the graph indicator. If I run this VI, you can see the data values in the waveform control are shown as points in the graph, and the DT item determines the time interval between the data points. Notice how changing the DT here changes the time interval between points on the graph. Now let's examine a 1D array of waveforms. Notice that this 1D array contains three waveform elements. All three waveform elements contain the same T0, initial time, and DT, interval time. The 1D array waveform control passes its data directly to the graph indicator. I'll run the VI. The graph displays each waveform in the array as a separate plot. Let's see what happens if I change the dt, interval time, of one of the waveforms and run the VI. Now let's see what happens if I change the T0 of one of the waveforms to 1 second later and run the VI. If you are acquiring a one-channel, one-sample data set, it will typically be returned as a DBL numeric data type. If you are acquiring one channel and sample, in other words, a multi-sample data set, it will typically be returned as either a 1D DBL array or a waveform data type. This VI acquires and displays one channel and sample data as a waveform data type. Notice that the DACMX read is configured for single channel, multiple samples in waveform. I can visualize this data as a regular waveform indicator or in a chart indicator, which shows a history of data written to the chart in previous loop iterations. To configure how much historical data a chart can show, right-click the chart, select the chart history length, and change the history length. The default value is 1,024 points. I can also visualize this data in a graph indicator, which shows only the multiple samples for the current loop iteration. Let's run this VI. The waveform indicator shows one-channel n-sample data for the current iteration. The chart indicator shows historical data, the most recent 5,000 samples, in this case 5 seconds of data. The graph only shows 1,000 samples from the current loop iteration, in this case 1 second of data. This VI acquires and displays one-channel n-sample data as a 1D DBL array data type. Notice that the DACMX read is configured for single-channel multiple samples and floating point data format. I can visualize this data as a 1D DBL array indicator or in a chart indicator, which shows a history of data written to the chart in previous loop iterations. To configure how much historical data a chart can show, right-click the chart, select the chart history length, and change the history length. I can also visualize this data in a graph indicator, which only shows the multiple samples for the current loop iteration. Let's run this VI. The 1D DBL array indicator shows the one-channel n-sample data for the current iteration. The chart indicator shows historical data, the most recent 5,000 samples. And the graph only shows the 1,000 samples from the current loop iteration. Graphs and charts include tools to help you zoom in on data, add cursors, and change plot styles. To zoom and pan on a graph or chart, right-click the graph and navigate to Visible Items Graph Palette. Click this button to zoom. I'm going to choose to zoom horizontally and drag the area to zoom. Click this button to pan. Click this button to zoom to fit all the data on the graph. To add cursors, right-click the graph and navigate to Visible Items Cursor Legend. Right-click the Cursors pane and select Create Cursor. Choose the appropriate options for you. In this case, I'm going to select Single Plot. And you can give it a descriptive name. Right-click the cursor to configure it. You can choose the cursor color, cursor style, or point style. Select Bring to Center, then slowly move the cursor. As I move my cursor, notice that the X and Y coordinate values update in the legend. Right-click the graph and open Properties. Notice that I can configure the display format, label and grid visibility, tick marks, auto-scale settings, and more for each axis. Now let's look at how to process one-channel n-sample data when it's represented as a waveform data type. If you use a math function, such as an add function, to add a waveform with another waveform, the add function adds each corresponding point from each waveform together. When you add a sine waveform with a noise waveform, the result is a noisy sine waveform, as shown in this example. When performing a math operation on two waveforms, make sure that both waveforms have the same dt, or interval time, and the same number of data points, y array length. Let's look at how to process one-channel n-sample data when it's represented as a 1D DBL array data type. In this example, the DAC-MX read is returning a 1D DBL array data type that represents one-channel n-sample data. If you use a math function, such as an add function, to add a 1D DBL array and a scalar, like a single numeric, the add function adds the scalar value to every single data point in the 1D DBL array. The original waveform contained a sine signal, so when you add a scalar 3 to the 1D DBL array, the result is the entire waveform is offset by a value of 3. If you use an add function to add a 1D DBL array with another 1D DBL array, the add function adds each element pair together, but it will only do this until the last element in the shorter array. Notice in the second example, the top array has 3 elements and the bottom has 4 elements, so the array result only contains 3 elements. In this example, the filter analysis VI receives 1D DBL array data from the DAC-MX read VI. This VI also provides the sampling frequency from the DAC-MX task properties node to the filter analysis VI. If you are acquiring n-channel one-sample data, it will be returned as a 1D DBL array data type, where each element represents one sample from each channel. This VI acquires and displays n-channel one-sample data as a 1D DBL array. Notice that the DAC-MX read is configured for multiple channels, single sample, and floating point data formats. I can visualize this data as a regular 1D DBL array indicator or as a chart indicator, which shows a history of data written to the chart in previous loop iterations. For this n-channel one-sample 1D DBL array to show up correctly as separate plots in the chart, you must add an array-to-cluster function between the array and the chart. Let's run this VI. The 1D DBL array indicator shows the n-channel one-sample data for the current iteration. The chart indicator shows historical data and a separate plot for each channel. This VI acquires and displays n-channel n-sample data type as a 2D DBL array. Notice that the DAC-MX read is configured for multiple channels, multiple samples, and a floating point data format. I can visualize this data as a regular 2D DBL array indicator or in a chart indicator, which shows a history of data written to the chart. To configure how much historical data a chart can show, right-click it and select Chart History Length and change it. I can also visualize this data in a graph indicator, which only shows the multiple samples for the current loop iteration. For this n-channel, n-sample 2D DBL array to show up correctly as separate plots in the chart, you must add a transpose 2D array function between the array and the chart. To configure the DAC-MX channel control to specify multiple channels, I can use the syntax AI0:3 to select channels AI0, AI1, AI2, and AI3. Now let's run this VI. The 2D DBL array indicator shows the n-channel n-sample data for the current iteration, and each row represents a separate channel's data. The chart indicator shows historical data, the most recent 5,000 samples per channel, and a separate plot for each channel. The graph only shows the 1,000 samples per channel for the current loop iteration, and a separate plot for each channel. Because n-channel data is represented by a 1D waveform or a 2D DBL array data type, you can manipulate the data using the array functions. The build array function concatenates multiple arrays or appends elements to an n-dimensional array. Pay attention to the difference in the thickness of output wires for the two build array functions. Refer to the LabVIEW help for more information about common array functions. In this example, the DACMX read VI returns n-channel, n-sample data as a 1D waveform data type. We can extract one channel's data by using the index array function. The index input specifies which channel to extract. For loops and while loops can configure an input tunnel to iterate through an array. When working with an n-channel array, a common task is to run the same processing algorithm on every channel of the n-channel data. To do this, we can use a for loop with auto-indexing tunnels. For loops and while loops can configure an input tunnel to iterate through an array's elements and configure an output tunnel to build an array. This is known as auto-indexing. While working with an array, you might want to access every element of the array individually. You can use a for loop with an auto-indexing input tunnel to process one element of the array during each iteration of the loop. In this case, there's no need to wire the end terminal of the for loop. The for loop will execute the exact number of iterations necessary to iterate through each element of the array. This example has a 15-element array wired to the auto-indexing input tunnel, so the for loop will execute 15 iterations, with each iteration extracting the next element in the array. A for loop with an auto-indexing input tunnel behaves similarly to a for each loop in other programming languages. If the n input is wired, and multiple arrays of different sizes are wired to the auto-index tunnels, the for loop uses the smallest of the choices to determine the number of loop iterations. For example, this VI has an n input of 10, a 5-element array, and a 3-element array. The for loop chooses the smallest of these, which is 3, and executes only 3 loop iterations. The final iteration indicator shows 2 because the iteration terminal starts counting at 0. If you want to collect the result of each loop iteration in an array, set the output tunnel append mode to indexing values to pass an array of those values out of the loop. If you want an output tunnel to return only the value from the last loop iteration, set the output tunnel append mode to last value instead. To configure the behavior of an output tunnel on a loop, right-click the tunnel and navigate to tunnel mode. Additionally, you can determine which values to write to an auto-indexing output tunnel based on a condition. To do this, right-click the auto-indexing output tunnel and navigate to Tunnel Mode and select Conditional. Now the auto-indexing output tunnel will only store a value if the conditional input is true. In the following example, only values that are less than 5 will be written to the auto-indexing output tunnel. Now that you know how to use for loops with auto-indexing tunnels, you can use this technique to iterate through each channel in an n-channel data array, process each channel, and output the processed results of each channel to another array. This example acquires n-channel, n-sample data as a 1D waveform array data type. It displays the acquired data in this graph. The multiply function can accept the 1D waveform array data type and scale all the channels before outputting them to the scaled channels graph. The filter VI is also able to accept the waveform data type and outputs the filtered data to a filtered channels graph. The RMS VI does not accept the 1D waveform array data type, so we can process every channel in the 1D waveform array by using a for loop with an auto-indexing input tunnel and an auto-indexing output tunnel. This outputs the RMS values for all channels to the RMS values 1D array indicator. The DACMX channel control is set to acquire channels AI0, AI2, and AI3. Now let's run this VI and see the results. Here's the acquired data for all 4 channels. Here's the scaled data, which has been multiplied by 100. Here is the filtered data for every channel. And here are the RMS values for every channel. This example generates a voltage ramp on an analog output channel. In this example, we want a linear ramp of 11 voltages, starting from 0 volts and ending at 5 volts. We also want this VI to output each voltage for 1 second. We can use the ramp pattern VI to programmatically generate a 1D DBL array that contains our ramp values. Then we can wire this array to an auto-indexing input tunnel, and the for loop will write each ramp value to the analog output channel. We can place the wait function to set how many milliseconds we want the voltage ramp to stay at each ramp value. Lastly, we can use a DACMX write VI before the loop to set the initial analog output voltage value, and use a DACMX write VI after the loop to set a shutdown analog output voltage value. This example outputs stimulus values on an analog output channel, waits for a defined settling time, and then acquires the corresponding response values on an analog input channel. The stimulus values array contains all the stimulus values, which is wired to an auto-indexing input tunnel. The for loop will read each stimulus value one at a time. For each for loop iteration, the auto-indexing input tunnel will output the next stimulus value and write it to the analog output channel, wait for the specified settling time, read the response value, and then write the response value to the auto-indexing output tunnel. After the for loop completes, the output tunnel will output all the response values. Additionally, this VI makes sure to write an initial value to the analog output channel and a shutdown value to the analog output channel. If you need to generate a waveform signal on an analog output channel, you can use a 1D DBL array. This example VI generates a user-defined sine wave on a DACMX analog output channel. The sine wave VI is configured to create a 1D DBL array of sine wave data points and sends it to the DACMX write VI, which stores these data points in a hardware buffer on the DAC device. Also, the sample rate is sent to the DACMX timing VI, which sets the rate at which the DACMX device will update the analog output channel's voltage. For example, if the sample rate is 10 Hz, the DACMX device will update the analog output channel every 0.1 seconds with the next data point. When the DACMX start executes, the DACMX device will output the data points specified by the 1D DBL array at the specified sample rate. The VI will then go to the DACMX wait until done VI and wait until the DACMX device has finished outputting all the data points. If you need to generate a waveform signal on an analog output channel, you can also use a waveform data type. This example VI generates a user-defined sine wave on a DACMX analog output channel. The basic function generator VI is configured to create a waveform data type of sine wave data and send them to the DAC-MX write VI, which stores the data in a hardware buffer on the DAC device. The DAC-MX timing VI here is configured to use waveform timing, so we'll wire the waveform into the rate input. This causes the DAC-MX timing VI to use the input waveform's DT to determine the rate at which the DAC device will update the analog output channel's voltage. You can use two for loops to programmatically create a two-dimensional array. In this example, the inner for loop creates an array with 4 elements. The outer for loop takes the output of the inner for loop, the array with 4 elements, and places it in a row in a 2D array. So the n input of the outer for loop determines the number of rows in the 2D array, and the n input for the inner for loop determines the number of columns in the 2D array. Here's a summary of what you've learned in this lesson.